Let's make an introduction to soil structure interaction right now. So we are going to, when we refer to soil structure interaction, we are going to say SSI. Soil structure interaction is basically what we are going to cover in soil structure engineering. I don't know why we didn't call soil structure interaction to this module, but this is the module. This is what is the module about. It's about the interaction between the soil and the structure. So in order to study this soil structure interaction, we need to know about continuum mechanics. Continuum mechanics is we are going to define after. Is an area of the mechanics that is something that we use a lot when we are doing computational mechanics. We have to study as well geomechanics. Is the mechanics of the soil. This is why it's called geomechanics. We need a little bit of tensor algebra. Tensor algebra because we need these entities, these mathematical entities that are called tensor, to describe the state of the stresses in different points of the system, structure and soil. We need to know soil mechanics, of course, because the soil has its own behavior and characteristics. So you need to know a little bit of soil mechanics to understand the problem and this interaction. We need to know about structures, and we need to know about the software we're going to use, because unfortunately for these problems that have this degree of complexity, we cannot run calculations by hand. We need to use a powerful software like ANSYS Workbench or any other software specialized in these kind of problems, because it's simply impossible to to face and to tackle the problems, because we are going to deal with several complex equations, and we cannot resolve it by hand. So in the first place, I want to define what is exactly this soil structure interaction we're talking about. So if you think, for example, in a building, let's say this building is founded by several piles, and this is a very it's just an approximation. I know this is not an structure. This is just a frame, but this represents an structure of a building. Let's say it's a tall building. I know you can see only 3 stories in here, but let's imagine that this is a tall building. So this pile will be in contact with the soil, and the soil will behave against the loads that are applied to the building, and they will be producing, between them an interaction. And this interaction is produced in the interface between the structure, between the foundations specifically, and the soil. So all these interfaces we have between this structure that probably will be reinforced with concrete and the soil, which will be a natural material, will be the areas where the soil structure interaction will happen. So it's a very, very thin, interface where a lot of things happens. I mentioned loads already because as engineers, as civil engineers and structural engineers, we are interested in the mechanical behavior of structures, isn't it? You know that because you've been studying structure for a period of time already. So, but when you talk about structures, you say, I'm interested only in the mechanical behavior. It is to say, what happens when I apply loads to an structure, the form. So I'm interested in knowing how much the form and how much stresses I have inside the different structural elements, and how much is the strain, just to be sure that the structure is not going to fail, because we, as engineers, we try to avoid avoid the failure of our structures. But when we talk about the soil analysis, we talk about loads as well, because the loads that are applied to the building will be transmitted to the soil, and the soil has to take these forces and has to spread these forces in form of stresses, as you can see in this diagram in here. So all these stresses are stresses produced by the contact between the structure and the soil. So the study of the loads are very important, because the loads are the ones who will produce the stresses in the structure, in the soil, and the interface between the soil and the structure. So what kind of loads we are going to take? We need to take charge of. We need to take charge of the self weight of the structure, of course, we need to take charge of the lead loads, the loads that are applied not all the time on the building, but for example the wind appear in some episode and some seasons of the year, and they can be stronger or they can be less stronger depending on the area, depending on the condition. But the wind is something that in tall buildings and in bridges, for example, is very important to take into account. We have as well variation of temperature. We don't usually take charge of these kind of loads, but they are loads because they produce stresses and they produce deformation and strains. And in some structures, big structures or important structures like bridges or tall buildings, this is important, especially when the material we use to construct the building is a material that is sensitive to changes in temperature. For example, when we use steel or we use any other metal, the metal are very sensitive in terms of temperature and they will produce a lot of stresses, and we need to do this analysis. In soils, the temperature is important as well. The temperatures introduce stresses and changes in the content of water, for example. So the temperature is something to take into account as a source of loads in our systems. I will call system the system that form the structure, the soil, and the interaction. Freezing as well is a variation of temperature, and in some places where the weather is so cold in the north and in the south of the planet, this can be very, very important as well, because not only because the change in temperature, but the change in the state of the water. So if you have in a soil, for example, a certain amount of water, and you because the low temperature, the freezing of this water is produced, the water will increase the volume, and this will produce massive amount of stresses around the area where we have this water changing the state from liquid to solid. We have another source of load that we don't usually take in consideration when we're doing the mechanical analysis, but the rust and the salt attacks are loads as well on our buildings, and they are really, really important in some cases, especially when we have, for example, important structure like bridges made by metal, by steel, and in areas where the sea salt, for example, attacks constantly the structure. This is very important to take into account because the rust will reduce the capacity of our structure to take loads. Of course, earthquakes, which are dynamic loads, are important as well. And there are many, many other loads to take in consideration, but let's say these are the important ones we can think just in this introduction. So soil-structure interaction is the mechanical behavior of the structures and the way this affects to the soil. So when we talk about the soil, as a minimum requirement, we need to run what we call is a hydromechanical analysis, because the soil, as you know, is a natural material that is not only solid, but has as well water and pores. And actually the soil is made by particles. So we cannot disregard the effect of the water in the soil. You know that there is a principle called the effective stress that is especially important in soils. This is because this principle includes or cover the hydromechanical behavior, we say in computational mechanics. So when we deal with soils, it's a little bit more complex because we are not talking about the mechanical interaction between forces and the formation in our material, but the hydromechanical, because water have a role to play, which is very, very important. Actually, if we do a more complex analysis in soils, you have to take into consideration the temperature, as I said before, and you have to take into consideration as well the chemicals that affect the soil in some way. So there are analyses that are called thermo-hydromechanical chemical analysis. We are not going to deal with that, don't worry. We are going to deal only with hydromechanical analysis because these are the minimum we need in our cases. And sometimes even only doing a mechanical analysis of the soil is enough because we, for some reason, we are not interested in complex interaction with water. So the soil and the structure and the interaction is a system. We are going to call this a system. So the interaction is the relationship between the structure and the soil, of course, because this is the relationship that is generated in the interface between the piles, for example, in this case, and the slabs in here, the raft with the soil. The problem is that the relationship in this interface is certainly complex. If we want to, let's say, to face this in a proper way, but we can make simplifications anytime we want in order to face and to tackle this problem. So I wanted to ask a question here. So this is a typical frame you will analyze very easily because you are all engineers and experts in structures. So if I give you this frame, for example, this frame with two fixed support in here, do you think there is any sort of soil structure interaction in this kind of schemes, in this kind of, let's say, yeah, this is on a scheme. If you have to resolve this structure and you calculate reactions, internal forces and diagrams and stresses, do you think we are taking in consideration the soil structure interaction in some way? Can someone tell me if you see in this scheme and in this kind of method you know how to use, if we are taking in consideration some sort of soil structure interaction? Because definitely these foundations in here are connected with the soil, isn't it? With the ground. There is an interaction because we are doing a hypothesis in here. We're saying, okay, the foundations in here will behave as a rigid connection between the soil and the structure. So our hypothesis is so strong that is simplifying completely the problem of soil structure interaction. We are saying that we are able to connect this column to the soil and create a rigid support. This is what usually we do when we analyze these structures, and it's a very strong hypothesis. So the reality is that there is an interaction, and this restriction in here, this support is not going to be rigid, of course not, because the reality is absolutely different to our hypothesis. But what we are saying in here is that the module, the Young modulus for these supports in here, for this foundation, are infinite. So infinite rigid. This is the assumption. A first, approximation to reality could be, for example, okay, the reality is that there is not this rigid foundation, but what happens, for example, if we think, okay, we are going to connect the structure with springs. So this is another extreme, because, okay, we are going to have, let's say, a behavior for this spring expressed by this relation in here between the stresses and strains, and this matrix in here with certain elastic properties for these springs. And we are having a more sophisticated interaction between the soil and the structure. So you have the structure as usual, you have the interaction as springs in two directions, but you're still saying that the soil is rigid. But the constitutive relation is called the constitutive relation between the stresses and strains in the interaction is provided by these springs in two directions and expressed by this relation between these vectors and matrices in here, as you can see in the screen. If we go beyond and we try to complicate things and we try to approximate our model to the reality, we will say, for example, okay, let's introduce something more sophisticated than springs, and let's use this dashpot in here, for example, in combination with a spring. And we are going to start, complicating let's say the behavior of the interaction. And we are going to introduce more and more complex equation, because this is what we call viscoelasticity that probably you have covered in some other modules in structures. So when we have this kind of behavior between the deformation and time, we have what we call a viscoelastic model. So this is more complex. This is probably can be shaped in more closely to reality, but we're still saying that the soil is rigid, because these represent only the interaction between the structure and the soil. So what happened, for example, in a pile? You have a pile, you have loads, vertical loads, horizontal loads on the pile, and you have the soil in here, you have pressure because the soil, and you have an interface because there is always a small space between the pile and the soil. So what we are saying in our model, with scholastic model, is that we are going to have this interaction by mean these springs and these these elements in here, these models, these scholastic models that will represent the behavior in the interface between the structure, the foundation, the pile, and the soil. But we're still saying that the soil is rigid, and this is not the case because the soil is not rigid at all. Because we have the possibility of using a software, a sophisticated software, we can produce, for example, with the software, a soil model. So we are going to define, for example, the behavior of this soil. We are not going to say that it's rigid. We are going to say that the model for this soil has certain characteristics. For example, will be elastic, or will be viscoelastic, or will be plastic, or elastoplastic, or whatever. And we're going to model then the behavior of the soil. We're going to model the behavior of the interaction. And we're going to model the behavior of the structure all at the same time because we have the software. So basically, this is the situation we're going to have when we deal with the software and the possibility. But the complexity of every model for the soil, for the interaction or interface, and the structure will depend on the necessities we will have. Because sometimes we need more complex models, sometimes we don't need so complex models. The thing is we are going to have this approach, this is the most complex approach we can have, we will need to have more knowledge, and we will need to have more experience to do that. And in order to do that, we are going to need some elements. For example, we are going to need to know what is continuum mechanics, what is physiomechanics, what is tensor algebra, what is soil mechanics, what is structure, and software like ANSYS Workbench, for example, the software we're going to use.